Okay, hi everybody. So in today's lecture, we're going to be doing basically a review of probability for machine learning. So I assume a lot of you guys have seen at least basic probability theory before, but in today's lecture, we're going to be reviewing a lot of the key concepts, in particular because sort of the machine learning algorithms we'll be seeing from this point onwards are going to rely a lot on probability concepts. So sorry if you've seen all this before and are a little bit bored, but good to have it fresh in your minds. Okay, so a couple of important announcements before we get started today. The first is that the second homework is due in 1 week, so next Friday. You guys should already be able to do problems 1 and 2, so these are on nearest centroids and K and N, so we've already covered these. And problem 3 is going to be on a method called logistic classifiers, or logistic regression. We'll start these algorithms today, but by the end of Monday's lecture, you'll be able to do problem 3. So again, as always, highly recommend you guys start working on this early. It's about as long as the first assignment, but maybe a little bit more sort of in the details of these ML algorithms. Very important announcement here is that there's no in-person lectures next week. So no in-person class Monday, Wednesday, Friday. I'll be out of town for actually a machine learning conference, so at least it's class related. I'll record the lectures, post them on Canvas, send out an ed announcement. So yeah, just be aware, no in-person class next week. We'll resume in-person lectures the week afterwards, though, so it's just 1 week of sort of interruption here. Coming up soon is the midterm, so 2 weeks. I'll release more details on this in Monday's lecture. We'll kind of go over, how you should study for this exam, what sorts of things we'll be covering, so on and so forth. I plan on releasing a practice midterm exam plus solutions, so it's a great way to study for the exam. And so, yeah, more details on that coming soon, but yeah, just be aware this is coming up. And also another kind of admin detail here, the details about the course project will also be released early next week. Probably in Monday's lecture, I'll discuss this a little bit. One thing you should start thinking about now is forming teams. So it's a group project. You should get into teams of 3 people in the class. If you are struggling to find teammates, we will release a spreadsheet to help you guys sort of form teams. Again, don't worry about the details right now, but in Monday's lecture, we'll see more of what's expected of you in the project. But yeah, just be aware it's that point in the quarter where we got some things to start taking care of. Okay, so in today's lecture, we're going to see a couple of different ways of comparing classifiers. So we've seen this a little bit, and we're kind of wrapping up things from the previous lecture in this first section. After that, as I mentioned, we're mostly going to be talking about probability in machine learning. Why do we think about probability in ML applications? Basic probability review. And then at the very end, we'll do a quick introduction into logistic classifiers, and we'll continue that discussion in Monday's lecture. A couple of reminders of what we did in our last lecture. We've wrapped up our discussion of the K and N classifier. Again, this is a classifier that's more flexible than the nearest centroid algorithm that we saw, but it does require tuning this number of neighbors K, and this hyperparameter K can have a pretty significant impact on model performance. So there's a trade-off between sort of simplicity of nearest centroids and having to actually tune this K and N classifier. We also went through a derivation of the time-space complexity of various algorithms that we've seen. And again, we care about this analysis because we really want models that are able to scale well to large problems. So for instance, in machine learning, you might have a huge data set consisting of millions, maybe even tens of millions of data points with potentially very, very many features. And so if your algorithms scale poorly to these large problems, even if they get high accuracy, they're not very useful because we simply can't apply them to the data we care about. And then lastly, we introduced this notion of the curse of dimensionality. And the key intuition or idea here is that the amount of sort of space grows exponentially with the number of features that you have. So we saw this demonstrated with that binning classifier at the end of Wednesday's lecture. Really, this is a curse because we then need exponentially more data to really sort of explore the data space or sort of, have enough data to represent our problem well. So the key point here is that machine learning, fitting models in high dimensions with lots of features is just inherently very difficult. Okay, so we're going to continue here with a little bit more detail on time-space complexity of our classifiers. So just some reminders on notation. We're using n to represent the number of examples, usually training data points. We're using D to represent the dimensionality of every feature vector. And we're using C to represent the number of classes in our problem. And we typically make this assumption that we have a lot more data than, say, the number of neighbors in KNN, and a lot more data than the number of classes that we have in our problem. We're using big O notation to represent time-space complexity scaling, essentially how the algorithm scales in the worst case. And we're interested in both time and space complexity. We care about how our model runs in terms of actual time and how much memory it takes. And we're also interested in both the training and the prediction phases of using our models. Okay, in the last lecture, I introduced this notion of a majority classifier, but I've got an additional slide here. I think I didn't quite do it justice in Wednesday's lecture. So this majority classifier is a really simple baseline that we can use to essentially gauge what level of accuracy we should expect from our classifiers. So the way this majority classifier works is that we're always going to predict the most common label in our data set. And we're going to make an assumption here that the label frequencies in our training and testing sets are more or less equal to one another. The error rate of this classifier, just predicting the most frequent label, is going to be 1 minus max p, where max p is sort of the probability or relative frequency of the most common label in our data set. This is not sort of a real classifier. It always predicts the same label no matter what input we give it. But it's useful as a baseline, again, for just gauging sort of what accuracy level is actually good for our problem. And so, yeah, it's a good number to gauge things based on. So, for example, you might have a binary classification problem where the probability of seeing class 1 in your data set is something like 95%. So we might have some medical diagnostic task where 95% of your patients are healthy and 5% of your patients are sick. Well, if you just predict healthy for every patient, then you're going to have an error rate of something like 5%. It's obviously a bad classifier. It's not really doing anything, but it still gets, a fairly good error rate. And this is just because our data is sort of imbalanced. Most of the data is coming from this first class. But what this means is that any classifier we build, nearest centroids, KNN, more complex algorithms that we'll see later, should have an error rate at least as good as this baseline classifier. If we're doing worse than 5%, well, that means we're worse than kind of just randomly guessing. Okay, so a little bit more of a concrete illustration. Let's say you have training data with 100 different data points. 60 of these data points come from class 1, 30 of them come from a second class, and 10 of them come from class 3. The class probabilities then are just the relative frequencies of these various classes. So the probability of class 1 is 0.6, class 2 is 0.3, and class 3 is 0.1. The majority here is class 1 with a probability of 0.6. And that means the accuracy of this majority classifier that always predicts class 1, no matter what data point we give it, is going to be 60%. And the error rate, of course, is just 1 minus that of 40%. In general, if you have C equally likely classes, which is fairly common in machine learning data sets, so something like the MNIST data set, they're all equally likely to occur. The error rate of the majority classifier is then just 1 minus 1 over C. So if you think about it a little bit about why that is, you'll see that this has to be the error rate. So this is something like 90% for MNIST, so pretty bad error rate there, but something like 66% for this wine data set we had seen before. So again, any classifier we build should do at least as good as 90% error rate on MNIST, or at least as good as 66% error rate on the wine data set. So just to have it all in one slide, the classifiers we've talked about so far. We've got this majority classifier, which again, simple baseline, not really a real classifier. We have this binned classifier that's kind of like a histogram. It just bins our data based on where it is in the data space. It's a very simple baseline, but again, impractical for high dimensional problems, just due to this curse of dimensionality. We've seen nearest centroid classifiers, which have linear, very simple decision boundaries. And then we've seen KNN, which has these more complex decision boundaries. So let's go ahead and compare all these classifiers that we've seen so far, just to get a sense of sort of their relative strengths and weaknesses. So looking at the prediction space complexity, we see the majority classifier has essentially no cost. It's not really doing anything all that interesting. The binning classifier scales exponentially in the dimension of the space. So this is very bad scaling for our binning classifier. The nearest centroid algorithm scales linearly in the number of classes and the number of features, whereas KNN scales linearly in the number of features, but the number of training data points. So if we look down here at the error rates, we see that KNN can do a lot better than this nearest centroid algorithm, say. Something like a 20% error rate on MNIST for nearest centroid, but a 3% error rate on MNIST for KNN. But this comes at the cost of much worse scaling performance. We might have, say, 10 classes in our problem, but we might be training it on 1 million data points. So N typically is much larger than C. So even though, again, you get typically better performance, or at least on par performance with KNN, you pay the cost of having much longer training times and typically much longer prediction times as well. So again, good to review this table, just make sure you understand where all of these different values are coming from. Another axis along which we can compare classifiers is how they scale with how much training we give them. By scale here, I mean not in terms of prediction time or training time, but how the actual error rate varies as we give the models more and more data. So on the x-axis here, I have the number of training data points, n, and on the y-axis here, I have the error rate of my classifier. And what we can see is that as I increase the amount of training data, my KNN model approaches an error rate of about 0 on this data set, which is the MNIST data set. In contrast, if we fit the nearest centroid classifier on this data, we see that it decreases for a little while as we give it more and more data, but essentially it flattens out and kind of asymptotes. And this is because our nearest centroid algorithm is just kind of too simple. No matter how much data we give it, no matter how much information it's seen, it's just never going to be able to produce decision boundaries that are complex enough to actually fit this data set. Got another example here on the wine data set that shows a little bit different behavior. So again, it's the same graph, number of training points and classifier error on the y-axis. But what you should notice here is that for small amounts of data, the error rate for KNN is much worse than the error rate for the nearest centroid algorithm. So even though KNN is more flexible than the nearest centroid algorithm generally, if you have a very small amount of data points, say 20 to 25 data points, the nearest centroid algorithm might actually outperform the KNN algorithm. Again, this is just because it scales differently with the amount of training data. It's sort of easier to learn the nearest centroids than it is to fit a KNN algorithm. Okay, so any questions on comparing classifiers? Okay, cool. So now we'll start sort of the main content of today's lecture, which is a review of probability in machine learning. So why do we actually need to use probability in ML in the first place? Aren't we happy with KNN and nearest centroid? And the real reason we want to work with probabilities is that the real world and real data is really full of uncertainty. This uncertainty comes from a whole host of different places. The first is that whatever process you're interested in modeling, whatever predictions you're interested in making, might just be inherently random. There's actually things out there in the world that aren't deterministic. But even if things aren't random, there are processes that are just so overwhelmingly complex that we have sort of no way of accurately modeling these problems. So imagine trying to predict whether or not someone has a disease based on their genetic code. Just an inherently very complex and very difficult problem. And so any predictions we make, there's going to be some uncertainty associated with that prediction. Another way uncertainty can come into a machine learning framework is if we have a lack of knowledge about a problem. So even if we go out and collect data, we might not have collected sort of the right data for our problem. There might be more information that we're just simply missing in order to make predictions. And modeling this uncertainty is really critical in many applications where we'd like to deploy ML algorithms. So for example, if we're classifying whether or not a patient has a disease, it's not really enough for us to just predict a label for this patient. I don't want my algorithm to say, yeah, this person has a disease or doesn't have a disease. I also want to know how confident my algorithm is. There's a difference between my algorithm saying you have a disease and I'm 50% sure versus my algorithm saying you have a disease and I'm 99% sure. So modeling this uncertainty is really critical in particularly safety-oriented domains like medicine or autonomous driving. And to actually work with uncertainties, we're going to use the language of probability theory. The reason we use probability to model uncertainties is that it gives us a very nice quantitative and very general framework for handling uncertainty. One of the benefits of quantifying uncertainty, putting numbers to it, it gives us rules for computing and manipulating these uncertainties. And of course, then we can use these tools to build ML algorithms that actually incorporate randomness and can model these probabilities. Okay, so let's jump into some basic probability theory. Again, this is hopefully review to most of you. We're going to call S, capital S, some space of events that we're interested in. And this is kind of all the possible outcomes of some experiment we could think about going and running. We're going to use capital A then to represent a particular subset of S, some event that we're interested in. So for example, we might have some kind of experiment corresponding to flipping a coin 5 times. Our event space, the total space of possible outcomes, is all head-tail strings of length 5. And an example of an event we could be interested in is maybe a particular string of head-tails. So here we've got head, tails, tails, head, tails. This is one outcome of my experiment. But it could be something a little more complex. It could be something like, what's the probability that I get heads on the first flip? Now, this is a collection of events in this space S, not just a single particular event. Something in the same vein is, more heads than tails. This is another event we might be interested in that falls in this kind of coin flipping experiment. And then we're going to use P of A or PR of A to represent the probability of seeing that particular event A. So you should think of this as if I randomly pick an element from my set S of possible outcomes, how likely is it to come from this subset A? So for example, S here again represents flipping a coin 5 times. A could be heads on the first flip. And the probability of this is, of course, 1/2. So if you think about this for a second, you should be able to convince yourself that this indeed should be 1/2. So I really like to think about a lot of concepts in machine learning in a very geometric way, and probability is no exception here. You can really think of the probability of an event A as sort of the area of A in our total space of outcomes S. So you can imagine our sort of experiment space being some box of outcomes, this blue box, A being some subset of this set of possible outcomes, and the area of A in S, sort of relative to the space of total outcomes, can be represented as its probability. Okay, so some basic axioms of probability theory. What are the rules of probability? The first is that for any event A, this probability needs to be between 0 and 1. It needs to be bigger than 0 because, again, thinking kind of geometrically, the fraction of the area corresponding to an event A can't go below 0. It's a fraction. And of course, it can't go above 1 because, again, it's a ratio between the area in A to the area in S. The probability of the whole space, S, has to be 1. If we randomly select an element from S, the probability that that element is in S should be 1. And the probability of no event happening is 0. So we have to pick some event, essentially. And then the last basic rule we'll need is the following. So there's a lot of symbols here, but we'll break down what's happening. On the left-hand side, we have the probability of A union B. And really what this means is, what's the probability of A or B happening? Really, this is sort of the total area corresponding to these two different events, A and B. So I've got them illustrated on the right-hand side here. A is this kind of red box, and B is this kind of yellow box. We want to know, what's the probability of seeing something from either A or B? This, of course, is the probability of A, so it's sort of the area of A, plus the area of B. But then we need to subtract off the intersection of these two areas. We need to essentially account for the fact that we're double counting this region here, where both of these events are happening simultaneously. So this is just a rule for computing sort of probabilities of simultaneous events. So for another, more visual illustration, we kind of want to compute the area of A union B, which is, take A and B, glue them together. This is the same as computing the area of A plus the area of B. And then we double counted this intersection, so we've got to subtract it off to account for that. Again, just a useful rule for computing probabilities. Okay, any questions on sort of the basic setup so far? We're going to go into some more details about some more probability topics, so yeah, it's important at this stage that you guys are following along. Cool. Okay, so the next concept I'll introduce here is the notion of a discrete random variable. So a discrete random variable, which I'll write as capital X, which may be a little bit of bad notation. Don't confuse this with a data matrix. I'm using X to represent a discrete random variable here. And this capital X is representing the outcome of some particular experiment. It's discrete in the sense that X can only take values in some finite set of possible outcomes. And this finite set is going to be disjoint and exhaustive. So X has to take exactly one value from this set of possible outcomes. So for example, S could represent the outcome of a single coin flip. We either see heads or tails, and this is again like a sample space S. A random variable X could then represent the outcome of this particular coin flip. So it's random because every time we run this experiment, we'll see a different outcome. A little bit more generally, a discrete random variable X can take values in some set capital S of discrete possible outcomes, A1 through AD. And to each of these possible outcomes, say A sub I, we can assign to it a probability. So this is the probability that X takes the value A sub I in this set. Essentially, think of this as, how likely is it that X takes this particular value? Using our basic rules of probability, we see that it needs to satisfy a couple of constraints. The first is that this probability, of course, needs to be between 0 and 1. Probabilities always take this range. But we also see that if we sum up all of these probabilities, it needs to be equal to 1. This is because the probability of this whole set, S, has to be 1. It's the whole sample space. X always has to take some value in here. And this sum on the left-hand side just represents, the probability of X taking any possible value from S. So again, probabilities are bounded between 0 and 1, and they sum up to 1. A little bit more generally, if we have any subset A of S, any collection of events here in S, the probability of this subset, probability of X coming from A, we can obtain this by just summing over each of the individual probabilities in this subset A. So really knowing the probabilities on the individual outcomes tells us the probabilities of any arbitrary event we might be interested in. This function, P of X equals AI, is called the probability mass function associated with this random variable, oftentimes just shortened to PMF. And again, it really tells you how likely each possible outcome is. Okay, let's see a couple examples of common random variables that you'll see in machine learning. The first is called the Bernoulli random variable. This is a random variable that can only take two possible values, either 0 or 1. We can, of course, specify the PMF of this random variable by just specifying essentially two numbers. The probability that X equals 1, which I'll call rho, and the probability that X equals 0, which, because these numbers need to sum up to 1, has to be 1 minus rho. So really, this is the simplest discrete random variable we can come up with. It's just representing a coin flip, essentially. Another random variable you see pretty often are binomial random variables. So I'll use the notation binomial p comma n to represent tossing a coin n times, where the probability of heads is p. Then a new random variable y is essentially the sum of the number of heads that I saw. So again, counting the number of times I see heads in a series of n coin flips. Okay, another class of discrete random variables that'll come up pretty often are called discrete random variables or categorical random variables. It's like a coin flip, except instead of only two outcomes, 0 and 1, we have d possible outcomes, 1 through d. So if you like sort of concrete visual examples, you can imagine this as being like a d-sided dice roll, where we allow different probabilities for each of the sort of potential outcomes. So associated to each outcome, say x equals 1, there's a probability p sub 1. For the dth outcome, there's a probability p sub d. And again, these all need to sum up to 1 to be a valid sort of probability distribution. And then sort of analogous to the binomial distribution that we saw, there's this multinomial distribution, where we essentially repeat this discrete sort of experiment n times and count up the total number of outcomes. So if we roll our dice n times, we'll get essentially a vector of counts corresponding to how many times we saw that outcome 1, how many times we saw the outcome 2, how many times we saw the outcome up to d. So really these are the four most common types of discrete random variables we'll see, and a lot of different problems can kind of be fit into these four categories. Okay, so the Bernoulli distribution is one that we will probably work the most with in this course. Typically we can represent the PMF of a distribution as a table of numbers. Essentially, what's the probability associated with each possible outcome? But sometimes it's actually useful to write down these PMFs as sort of functions. This is useful because we can then sort of take derivatives, write nice formulas about them, so on and so forth. So for an example of how you can write a PMF as a function rather than just a table of numbers, let's say we have a Bernoulli random variable taking values x equals 0 or x equals 1. We'll often write something like p of x for the PMF. So this is like, what's the probability that x takes value little x? And for a Bernoulli random variable, you can write it as rho to the x times 1 minus rho to the 1 minus x, where again, rho is essentially the probability of seeing heads on my coin flip. So if I plug in x equals 1, this is the heads outcome, and evaluate, you'll see that this evaluates to just rho, and if I plug in x equals 0, we'll see this line evaluates to 1 minus rho. So again, it's a function that I can plug in essentially the outcome to and get out the associated probability value of that PMF. Another concept we'll need to make use of are joint distributions. So joint distributions are essentially a way of modeling the outcomes of two random variables simultaneously. So when I write the probability that x equals x and y equals y, I mean I have two random variables, x and y, and I'm seeing what's the probability that x takes value x and y takes value y simultaneously. So like I have two coins, I flip them at the same time, what's the probability of seeing a particular outcome? Oftentimes we can, again, write these as probability mass functions, just assigning some probability to each possible outcome here. And again, we can often express these as a table of joint probability distribution values. And we'll see some examples of these later. Again, if we sum over all of the possible outcomes, it's now a sum over both x values and y values, but this has to sum to 1 to be a probability distribution. A very useful sort of rule or law for computing things in probability. It's called the law of total probability. And what this says is if I have some joint distribution, p of x comma y, to get the probability of seeing an outcome x, I can sum over all of the possible outcomes for y. Okay, this might look a little unnatural at first, but I think it's fairly intuitive if you break down what's happening here. So we're interested in the probability of some outcome just about x. We don't know what value of y occurred in p of x. In fact, we don't really care what value of y occurred, but we know some value of y had to have happened. But since we don't know which one happened, we can just sum over all the possible y outcomes, and in doing so, we'll get the probability of x. So for example, if you have some binary value for y, the probability of seeing a value for x is, okay, what's the probability that I saw x while y was 0, plus what's the probability that I saw x while y is equal to 1. You know, these are really the only two possible cases here. There's no other y values that y could take. So of course this has to be the probability of just seeing x in the first place. Okay, so let's look at a more concrete example here to just illustrate these concepts a little bit further. So say we've got some example about going to the dentist, where t is a binary random variable representing whether or not a patient has a toothache. D is a binary random variable representing whether or not a dental probe catches. So I guess you have some tool stuck in your mouth and there's some outcome whether or not it passes some kind of test. And C is a representation of whether or not this patient has a cavity. So again, another binary random variable. Let's focus on this table on the right for just a second. By representing a PMF as a table, what I really mean is that to each possible value of my random variables, I associate some probability of seeing that combination of random variables. So the probability that a patient comes into my dentist office, has no toothache, does not have a dental probe catch, and does not have a cavity is something like 57%. So this is the probability associated with this sort of joint event over possible outcomes. For another example, if a patient comes in with no toothache, the dental probe does not catch, but they do have a cavity, this has a smaller probability of about 0.8%. And if you sum all the numbers in this final column, you'll get a value of 1. Because again, these are all of the possible outcomes of sort of my experiment here. Okay, let's see a demonstration of this law of total probability that I showed you guys on the last slide. Let's say we want to figure out, okay, what's the probability that a random patient comes into my office and has a cavity? So P of C equals 1. Well, to compute this, I can just sum over all of the patients, regardless of whether or not they have a toothache and whether or not this dental probe catches. So this should be a D down here. Again, the idea is I don't care about these other variables, I just want to see whether or not this person has a cavity, so I can kind of account for all the other cases. And if you look in our table, we essentially want to add up all of the probabilities whenever C is equal to 1. So these are the highlighted rows in the table where these numbers are coming from. So I just sum up all the scenarios where the person has a cavity to get sort of the total probability associated with having a cavity. And this value here is going to be 0.2. Okay, the next concept we'll need are conditional probabilities. So conditional probabilities are quite important concept. And the idea here is that they represent the distribution of some random variable, given that some other random variable takes a very specific fixed particular value. So one thing we'll introduce real quick here is called the chain rule. So for a joint distribution over x and y, we can also equivalently write this as the probability of seeing x occur times the probability of seeing y occur given that x occurred. So for example, the probability that it's raining and cloudy simultaneously is what's the probability that it's currently cloudy times the probability that it's raining given that it's cloudy. So it's a way of sort of factorizing joint distributions into what's called the marginal, so essentially the distribution over the individual x, and the conditional distribution, which is the probability of y given that x has occurred and has taken some particular value. Let's see, this is what I said. If you sort of rearrange this chain rule equation a little bit, you can write that P of y given x is the same as this joint distribution divided by the value for P of x. That's a nice formula for writing down conditional distributions. You can, of course, do this for more than 2 random variables. So if we've got 3 variables, x, y, z, we can write down a chain rule of this form. If we've got 4 random variables, you can write down a chain rule of this form. Essentially, you kind of condition on things you've seen previously. So we've got P of x, and P of y given x, and P of z given x and y. In this class, we won't have to worry too much about chain rules of this form, but yeah, make sure you understand this chain rule for at least 2 random variables. Okay, so let's see how we can use these conditional distributions to sort of ask queries about our random variables that we might care about. So going back to our dentist example, recall from the previous slide we calculated that the probability that a random patient comes into my office and has a cavity is 20%. But let's say that a patient comes into our office, and we don't know whether or not this patient has a cavity, but we do know that the dental probe did not catch and they don't have a toothache. So how does this change our belief about whether or not this patient actually does have a cavity? We've got some additional information about this person that should update our beliefs. In the language of probability, what I want to do is calculate this conditional density. So what's the probability that C equals 1 given these other 2 outcomes? Okay, so if I just plug into that formula for the chain rule from the previous slide, I'll see it's the ratio of the joint distribution of these 3 variables divided by essentially the probability of my conditioning variables. Okay, so I can just look these numbers up in my table, essentially. So this top one, PC equals 1, D equals 0, and T equals 0. Let's see, where is that in my table? Somewhere in my table. I think it's this line here, yeah. So this is the numerator. The denominator then, well, we need to sum over the possible outcomes for C, because we essentially need to get rid of that C variable. So we sum up the probabilities in these two rows to get the probability of D equals 0 and T equals 0. Okay, and if you plug all those in, our new sort of probability of this person having a cavity, given our evidence, is a lot smaller. You know, it goes down from a 20% chance of a patient having a cavity down to about sort of a 0.012 probability that that patient has a cavity, you know, given that we did these sort of tests on them. We do the same calculation, which I encourage you to go ahead and do when you review these slides. Make sure you understand where these numbers are coming from. But what we should note is that if the dental probe catches and this person has a toothache, well, our sort of belief about whether or not they have a cavity goes up to 87%. So again, this is important here because it allows us to sort of compute beliefs about things given evidence about other variables. Oftentimes these are called posterior probabilities. The idea is we observe some evidence and what's our sort of belief about some variable we care about posterior to seeing this new evidence. So here's another example calculating this. I'll go kind of quickly through this because it's in the same vein, but I really encourage you guys to make sure you understand where all of these numbers are coming from and that you can now reproduce these calculations. So here, instead of observing D, I only observe T equals 1. So I didn't do my dental probe test. They just have a toothache. Using my chain rule, I can write this is the joint distribution over the marginal distribution. And then sort of using that law of total probability, I can look up the corresponding rows in my table, get these numbers, and compute a 60% probability. So again, make sure you go back through these slides and can do this calculation yourself. I'll point out here that the number on the bottom of this fraction, P of T equals 1, is called the probability of evidence. So really it's, what's the probability of seeing my evidence here that I saw for this patient? Okay, and then next up, another concept from probability that's very, very useful in machine learning. It's called Bayes' rule. So this is a pretty old concept in probability, named after Reverend Thomas Bayes from 1700s. And essentially from the chain rule that we saw before, we know that a joint distribution over x and y, so the probability of seeing x and y simultaneously, can be factorized as a product of the marginal p of x times the conditional p of y given x. And of course we can sort of factorize this the other way as well. It could be written p of y and p of x given y. But essentially, Bayes' rule, all this says is how we can calculate the posterior of some event given some evidence. So if I observe that x occurs and takes some value, what's the probability that y takes some value? It's essentially saying I have some evidence about something and I want to compare that to my belief about some other variable I care about. And just from the chain rule, we can write it in the following form, which is the product of the conditional distribution, but now kind of flipped around, times the marginal distribution for y divided by the marginal distribution for x. And again, this is very useful for computing probabilities. So let's see a kind of concrete example here. Let's say F represents whether or not some patient has the flu, and let's use H to represent whether or not some patient has a headache. Let's say we know that there's, say, a 95% chance that this person does not have the flu, and only a 5% chance this person has the flu. But let's say they come into our clinic and they have a headache. We're then interested in calculating, okay, what's the likelihood that they have the flu given that they do have a headache? So we know they have a headache, and we're trying to figure out whether or not they have the flu. We can use Bayes' rule to help us calculate this. So again, just plugging into this formula up here, essentially, we know that P of x given y, which is now probability of a headache given the flu, which we know from this table over here. And then we also need to multiply this by the probability they have the flu. We know that from this table. And at the end, we need to divide by this probability of evidence, P of x, which we can get from the law of total probability. So again, won't go through all the details of this calculation, but make sure you understand the steps here. Okay, so this is one of these things that is good to know about, but you won't be asked about sort of on an exam or anything like that. But we've now seen how to work with discrete random variables, i.e. random variables that can take only a finite number of outcomes. But what about random variables that take continuous values? So for example, x could be a random variable representing the temperature on some particular day. This doesn't just take discrete numbers, it can now be sort of any arbitrary positive number. But the problem is that expressions like the probability of x taking a particular value, little x, just don't make sense anymore. For example, there are continuously many values that x could be taking, sort of infinitely many values. And in order to satisfy the laws of probability, we would need to be able to sum up all of these values and get 1. And we just can't do that sum anymore. We have continuously many outcomes. So we need a new tool here that lets us work with continuous random variables. And these are called probability density functions. So one thing that is well defined for a continuous random variable is called the CDF, or cumulative distribution function. And this is the probability that x takes some value smaller than little x. So, what's the probability that the temperature tomorrow is going to be less than 70 degrees? The probability density function is then the derivative of this CDF. And you can really intuitively think about these as similar to the probability that x equals x, but it's not exactly the same. So think of P of x as like, what's the probability of seeing x, but not exactly. So one way this intuition breaks down a little is that we know that probabilities are between 0 and 1, but these probability density functions can actually take values larger than 1. The idea is they're kind of representing, how dense is the outcome around this particular point x. And if you want to get out actual probabilities, you need to integrate these PDFs. So again, don't worry too much about the details here, but it's just good to have heard, this PDF term and know how you might work with continuous random variables. So for some examples, we'll say that x is a continuous random variable with a uniform a comma b PDF if it takes values between a and b with equal probability. So if I pick a random number between 0 and 1, it's now a continuous random variable, and its PDF is going to look, something like this. It's basically flat because each of these outcomes are equally as likely. Another example that you guys might have heard of are Gaussian or normal distributions. These are the classic sort of bell curve distributions. And again, another example of a continuous PDF. So here's the formula for the density of a Gaussian distribution. Don't worry about the details here, just showing it so you've at least seen it. If you want to learn more about continuous distributions and continuous random variables, there's a really nice resource linked on the Canvas page. It's this book, Mathematics for Machine Learning. Freely available online, so you can just go download the PDF. And it really covers a lot of the details of probability that I'm glossing over here. If you're interested in kind of going farther in machine learning, I really recommend brushing up on your probability skills. It's probably one of the most useful things you can pick up on if you're interested in ML. Okay, so that concludes our probability review. Do you guys have any questions? Yeah. Yeah, I think your intuition there is right. Maybe ask me after class and we can sketch out exactly for that example. But yeah, the idea for, again, the chain rule is that you can kind of decompose the outcome of two random variables happening simultaneously into kind of a sequential thing. So on the left-hand side, I say, what's the probability of x and y happening simultaneously? Well, this is the same as the probability of doing my experiment X and seeing that outcome X, and then seeing that X occurred, what's the probability that Y occurs afterwards? So you're kind of breaking down a simultaneous experiment into a sequential experiment. And these have to be the same, is what the chain rule says. Yeah, in the back. Yeah, so you can certainly compute basically any kind of query like that you're interested in. So using all of these rules of probability that we went over, anytime you have a question like, what's the probability of seeing this particular set of outcomes, you can use these rules to compute that kind of stuff. And it all follows from these kind of basic but very general steps here. Cool, any other questions on probability? Cool. Yeah, so in this class we won't be going too heavy on the probability stuff. It's not a stats course, but it's good to at least understand the basic concepts here because we're going to be using the language of probability theory to start building ML classifiers. Okay, so in the last few minutes we're going to do a quick introduction to logistic classifiers. We're not really going to see the details quite yet, but just what's the intuition, what's the basic idea? And hopefully by the end of these slides, I can convince you guys that you could have invented this algorithm yourself. So let's say we have a binary classification problem. We're trying to predict a label y from some feature vector x. And we're interested in modeling the uncertainty about our prediction. What that really means is that in our language of probability that we have now, we're interested in the conditional probabilities. We want to know what's the probability of y equals 1 given this feature vector x. So I observe some information x, and I want to know what's sort of the distribution over labels. And then, of course, I'm also interested in the other outcome, but this is just 1 minus py equals 0 given x. So I just said this, it's sufficient to model just the first outcome here because it's a binary outcome. I can get the other probability by just doing 1 minus the first value. But the classifiers we've seen so far, k and n, nearest centroids, so on and so forth, don't produce probabilities. They just spit out a label for us. So we're going to need a new model in order to actually, somehow fit these uncertainties. And the key idea here is that for every feature vector x, we're going to produce some kind of numerical score using a function f of x with parameters theta. So again, here theta are some parameters of my model. I haven't said exactly what they are yet. But the idea is that high values for my function f of x are going to somehow indicate that y equals 1 is more likely for this data point x. And low values for f are going to indicate that y equals 0 is more likely. But here, we're not going to worry about modeling probabilities. We're just going to let f take arbitrary real values. But then, of course, to model probabilities, we need to somehow turn this arbitrary numerical score into a probability. So again, probabilities need to be between 0 and 1, so we'll need some method to somehow transform this score into this range 0, 1. Okay, so if we can execute this idea somehow, then we'll have a nice model that actually lets us fit probabilities. Okay, so the first step is how do we actually produce this real valued arbitrary number from our data x? So do you guys have any guesses on what I could do here? Yeah. Yeah, so it said regression, and it's exactly what we're going to do. So we saw regression models already, right? These are models that take in data and just predict some kind of real valued number. Well, maybe I can try and do that, but now fit it to a score, something that represents a sort of probability. So a really simple regression model that we already saw is linear regression, or linear models, where we just take sort of a weighted combination of some weights times my features. This is exactly what we're going to do to produce those scores. Okay, well, we've got our scores, and now we just need to turn them into probabilities.